Hello everyone, my name is Gautam, and in this video I'll be presenting our work on efficient object tracking using separable self and mixed attention transformers. To give a brief introduction of object tracking, let's assume that you are given a video, and in the first frame of the video a target object is annotated with a rectangular bounding box. The goal of the tracking algorithm is to estimate the trajectory of the target object in the given video. This task is particularly challenging because we do not have any prior knowledge of the target, and in the video the object undergoes various challenges such as deformation, motion blur, illumination changes, partial occlusion, and cluttered background. And the tracking algorithm is expected to overcome these challenges and accurately localize the target object. Among the various algorithms proposed for object tracking, the Siamese network-based approach with vision transformers as the backbone has shown state-of-the-art results over various benchmarks. However, these vision transformer-based trackers are computationally expensive due to a large number of model parameters, and they require specialized hardware such as a GPU for real-time inference. And when it comes to Siamese network-based lightweight trackers, these trackers underutilize transformers due to the computational complexity of the attention blocks. And since the architecture of these trackers is based on convolutional neural networks, they show suboptimal performance on the challenging datasets. And as a solution to this problem, we propose a transformer-based tracker which uses a separable attention, which is more efficient compared to the standard transformers. And our approach is able to run at a real-time inference speed on a CPU, while it outperforms the related lightweight trackers on 6 different datasets. To summarize our contributions, we propose a backbone which consists of a cascade of convolution and transformer blocks, and we use mixed attention to fuse the information from the template in the search regions in the backbone. Along with the backbone, we also propose a self-attention transformer-based predictor head, which effectively models the global contextual modeling of features for robust target state estimation. And with this combination of proposed backbone and the head module, we are able to achieve superior results compared to the related lightweight trackers. And the efficiency of our tracking approach enables our tracker to achieve a speed of 158 FPS on a GPU, whereas it also runs at a speed of 37 FPS on a CPU. This block diagram summarizes the architecture of the proposed separable mixed attention transformer based backbone. As we mentioned earlier, we use mixed attention to fuse the information from the target template in the search region in the backbone. So instead of using standard transformers, we use a separable attention block, which effectively computes the attention by using pointwise multiplication in comparison to the dense matrix to matrix multiplication in the standard transformers. For the neck module, we use a simple cross-correlation operation between the features that are generated from the target template and the search region. And for the proposed predictor head, we use a combination of convolution and transformer-based blocks for target classification and bounding box estimation. And we observe that this combination of CNNs and transformers is beneficial during target localization when the target object undergoes drastic shape variation and heavy occlusion. To summarize the training details, we use the combined videos from the GOT10K, TrackingNet, and Lasso datasets along with the images from the MS Coco to train our tracker. And we use loss functions for the classification and regression output generated by our tracker. And we use a we train our model for 300 epochs with AdamW optimizer. We set our batch size to 128 based on the maximum number of samples that can be fit on the GPU used during training. And the values of hyperparameters in the loss function are determined based on the values that are used by the related trackers. When it comes to the experimental results, we can see that the proposed tracker is the only one that concurrently deploys a transformer-based backbone and the predictor head. And when you look at the results, we can see that our tracker outperforms all the related lightweight trackers on 6 different datasets. And due to the usage of separable attention, which is more efficient compared to the standard attention, our tracker able to achieve is able to run at a speed much higher than the real-time speed on a CPU. And we conduct additional ablation studies in order to experimentally quantify the impact of different contributions. For example, in order to verify the impact of feature fusion in our tracker backbone, we retrain the network without fusing the features in the backbone, and we observe that the feature fusion improves the overall results due to the flow of information between the two branches of the network. Similarly, mixed attention is not the only way of using the feature. There are other options such as using cross attention or using a sequential combination of self and cross attention. And we observe that the sequential self and cross attention gives the best results. However, with mixed attention, which only approximates this operation, we observe slightly inferior results. However, in comparison, our mixed attention is around 50 times faster on a CPU, while with a drop in performance of around 0.6%. Similarly, we compare the performance of the proposed transformer-based predictor head with the pure convolution-based head module, and we observe that with the self-attention, we are able to capture long-range feature dependencies within the fused encoding, which results in superior tracking accuracy compared to the fully convolution-based predictor head. In order to better understand the working of our tracker, we visualize the attention maps for different challenging scenarios while tracking various target objects. And we observe that in all the scenarios, despite the target undergoing different challenging factors such as aspect ratio changes, illumination variation, deformation, and occlusion, our tracker is able to accurately focus on the target object and generate the appropriate bounding box results. And when compared to the state-of-the-art vision transform-based trackers, the results of our proposed approach is not on par. However, if you look at the results of the CNN-based state-of-the-art trackers from 2020, our approach is able to outperform those trackers with much lower number of parameters while running at a much higher speed on a CPU as well as GPU. And even when compared to the state-of-the-art vision transfer-based trackers, our approach is better suited for applications with constrained resources. To conclude, the state-of-the-art transformer-based trackers are computationally expensive due to the large number of parameters and the expensive attention operation. The proposed tracker deploys a separable attention-based backbone and head module, which is able to generate superior results when compared to the other related lightweight trackers. And in the future work, we are planning to deploy our tracking algorithm on embedded devices such as smartphones in order to measure the runtime memory as well as the energy efficiency. We have released the tracker code and the pre-trained models on GitHub. Please use the QR code to uh, access the code and the model. Thank you very much.